respected scientist believes an oceanic catastrophe threatens Earth. A massive release of volatile methane gas.
The damage will be of a scale which has not been observed ever.
A methane eruption may have caused the greatest mass extinction in Earth's history. If it occurred in the past, it could strike once more in the future.
There is no question in my mind that it will happen again.
Tsunamis inundate coastal cities, and lightning ignites clouds of explosive gas.
There will be huge fires, conflagrations, explosions.
Methane explosion on mega disasters. It's often called the Big Blue Marble. Planet Earth, sheathed in its cloak of life-giving water. But hidden at the bottom of its oceans, there could be a ticking time bomb. It is a vast reservoir of potentially dangerous methane gas. In the deep ocean, huge quantities of methane are held in solution with the liquid seawater, or frozen in ice deposits trapped in sediment. Normally, when methane bubbles up from the seafloor, most of the bubbles gradually disappear, because methane has the ability to dissolve into water. No different than salt or sugar. When it dissolves, it becomes invisible. Methane, the simplest of all hydrocarbons, is the main component of natural gas. It is both a resource and a hazard. Dissolved in water, it will not burn, but when it is released into the air, any spark can make it explode. This is what can happen when methane is ignited. The source of this 1994 explosion was an ordinary 36-inch natural gas pipeline in Durham Woods, New Jersey. It created a blowtorch of 1,500-degree flame, 600 feet high for 2.5 hours, until utility workers were finally able to shut off the gas flow. As spectacular as this seems, the amount of gas that caused it is minuscule compared to the explosive potential from methane in the ocean.
The total amount of natural gas, which is essentially methane, which was released in that fireball, is about 3 billion times less than the amount which would be released in a reasonable size oceanic eruption.
Dr. Gregory Riskin is a professor of chemical engineering at Northwestern University. He has developed a controversial theory that says the oceans can and have produced methane eruptions on a global scale.
It has happened periodically over the last half-billion years without fail. So there is no question in my mind that it will happen again.
Riskin believes that the worst methane eruption in Earth's history happened 250 million years ago, at the end of a time geologists now call the Permian period. Methane, says Riskin, was responsible for the Permian mass extinction, the largest mass extinction of all time.
What is the mass extinction? Some people say it's just when a lot of species go extinct suddenly. A lot. True, but that's not enough. Not only species, but groups of species, whole categories of species.
In the Permian mass extinction, up to 95% of all species disappeared from the face of the Earth. Today, many scientists call it the Great Dying, and they continue to debate its cause.
The terminal Permian extinction has bothered us paleontologists for 200 years.
In the past, researchers have theorized that the extinction was caused by an ice age or climate change due to movement of the continents. Perhaps an asteroid struck. nearby supernova in space, or widespread volcanic lava flows in Siberia. But Professor Riskin believes the extinction was the product of a giant methane eruption and its incredible explosive force.
The amount of energy which would be released in the combustion and explosion of the methane in a large eruption would be about 10,000 times greater than the total nuclear stockpile which is available at this moment.
Before the Permian extinction, the Earth was a very different looking planet than it is today. Most of the ever-drifting continents were fused together in one giant landmass called Pangaea. Long before the dinosaurs, tiger-sized finback reptiles lived among the primitive trees, while crocodile-like amphibians inhabited the swamps. An enormous planet-wide ocean was populated by ancient fish, corals, and other sea creatures. Species that would disappear between the end of the Permian and the beginning of the Triassic period.
In the times of Permian-Triassic boundary, the geographical situation was especially conducive to the stagnant ocean.
A stagnant basin in the lowest part of the ocean is one of the first ingredients in generating methane eruptions. Riskin's theory works like this. Deep pockets in the ocean allow methane to accumulate over long periods of time.
Perhaps hundreds of thousands of years, perhaps even a million of years. Until eventually the water will be essentially saturated with dissolved methane.
Methane itself comes from the seabed, where microbes dine on organic matter, producing methane as a byproduct. In most parts of the ocean, currents keep things moving, helping to provide oxygen for other microbes that consume methane, which keeps it from building up.
Most of the deep ocean is sort of ventilated. In other words, it's very sluggishly moving, but it is moving.
But where there is no motion, the ocean is stagnant, and the waters become anoxic, meaning they have little oxygen. So no methane-eating microbes can live there, and the gas slowly dissolves into the deep waters. It's well known that deep water creates high pressure, and the more water is under pressure, the more gas it can hold in solution. The pressure of the deep stagnant basins on ancient Earth may have set the stage for the methane eruption.
The concentration, the actual amount of methane molecules in a given volume of water can be 200 times greater near the seafloor than near the surface of the ocean.
In the Permian period, a seafloor basin of methane-saturated water may have reached a breaking point. An earthquake, underwater landslide, or even a meteor impact could have been the trigger. And suddenly, like shaking a gigantic soda bottle, the deepest part of the ocean would have exploded in a deadly storm of methane bubbles. The threat to life began below the sea surface, where the methane bubbles pushed huge quantities of oxygen-poor water upward. The effect was to suffocate marine animals on a wide scale. Then the churning methane gushed skyward, shooting huge fountains of gas-laden water into the air. A violent process that may have gone on for days or weeks. Methane is lighter than air and would normally float away, but in the chaos of an ocean eruption, the swirling clouds of gas and water stay low to the Earth's surface.
The expelled methane will be mixed with water droplets, and it's very important that it will be heavier than the air, so it will be hugging the Earth as it spreads. Now this explosive material is going to be ignited by lightning, and then there will be huge fires, conflagrations, explosions,
The shock of the ocean's eruptions also may have sent tsunamis crashing against Pangaea's coasts, drowning animals that lived on the shorelines. It would take the barren Earth 5 million years to regain the diversity of life it lost during the Great Dying. The mass extinction is an accepted fact, but the notion of a methane eruption as its cause is a radical idea with little acceptance in the scientific community. Much of the skepticism over Riskin's theory stems from the fact that no one has ever witnessed a methane eruption. Until recently, no one imagined that any kind of gas had the potential to generate such natural eruptions in water. But that changed in 1986, when a mountain lake in the African nation of Cameroon erupted in a deadly carbon dioxide gas explosion that was totally new to human experience.
We don't think of lakes as just rearing up and killing massive amounts of people. And so this was a very rare phenomenon.
The concept of gas exploding from bodies of water was suddenly plausible. If gas can create a killer lake, then why not methane in a killer ocean? The idea of a violent methane eruption from one of the world's oceans seemed like science fiction, until something very much like it actually happened. It took place at Lake Nyos in the African nation of Cameroon.
Well, in 1986 in Lake Nyos, something happened in lakes that had never happened before. There was a tremendous eruption of CO2 gas that was stored in the lake.
A huge fountain, driven by 1.6 million tons of carbon dioxide, shot out from the waters of Lake Nyos.
This gas, when it came out of the lake, produced so much energy that it generated a gas water fountain out of the lake that was about 100 meters high. And it filled up the lake basin, and because CO2 is about twice as heavy as air, it flowed out over the spillway and coursed down through the river valleys where it killed people up to 16 miles away from the lake.
1,700 local villagers and all their livestock died, smothered by carbon dioxide, which reached concentrations of nearly 100%.
In the atmosphere, carbon dioxide is in a concentration of about 0.03%, so 0.03%. Now, for humans, concentrations aren't dangerous until they get to about 10 or 15%. And at that point, they produce an epiglottal stoppage, so your air pipe shuts down very quickly, and actually you die from suffocation quickly.
History is filled with stories of volcanoes, earthquakes, and tsunamis. But no one had ever recorded anything like the gas explosion at Lake Nyos.
Part of why it seemed impossible for this to happen, this kind of an eruption to happen in the lake, was that it hadn't happened before.
At Lake Nyos, scientists discovered that far below the lake floor, a pocket of hot magma generates carbon dioxide gas that rises up into the lake bottom, where it continually dissolves in the water. The gas is stored in the high-pressure deep water. But if the pressure is ever released, the gas bubbles out. Exactly the same principle as in a bottle of champagne.
In any bottle with dissolved gas in it, like champagne, you don't see the gas because the pressure of the cap is forcing the gas into solution. However, when you take the pressure off of the gas, that is, you take the lid off here, then what happens is the gas is free to expand rapidly, and it produces this tremendous explosion. And you get the gas coming out of solution with a lot of expansion force.
In Lake Nyos, the weight of the water acted like the champagne cork, and a sudden disturbance released it. Kling and others believe a landslide may have been the trigger. But it was the gas itself that created the threat.
What happened at Lake Neos is that there were high concentrations of gas in the bottom water, CO2 that had built up over very long periods of time. And nobody really knew about it. We didn't know that it was so dangerous.
Dangerous gas under pressure in deep water was a rare phenomenon. But could it exist elsewhere? Apart from Neos, researchers found that gas is also accumulating in African lakes Monument and Kivu. The discovery led scientists to wonder whether this could happen again.
The eruption at Lake Neos really lit a fuse in the scientific community for an explosion of ideas about where else this might have occurred, and most specifically, whether there were these kinds of tremendous gas eruptions from the ocean.
But this idea that similar methane deposits in the ocean can cause catastrophic eruptions is yet to be accepted by mainstream scientists.
Now, at this moment, my theory is not very popular, which is completely understandable because of its kind of radical nature.
As a chemical engineer studying subjects normally in the realm of geologists and paleontologists, Professor Riskin faces a struggle for acceptance.
The work is not what I would say the most well-recognized or welcomed in the community. I can't say that too many people are citing this work and considering it credible.
Science has become so wide nowadays that there is nobody in the world who can understand all aspects of it. Now, when an outsider like me tries to sort of encroach on their turf, people react differently.
One objection to Riskin's theory is that the open ocean can't keep methane bottled up enough to reach explosive proportions.
You can't build up a lot of methane in water because eventually you have so much methane that it can diffuse out. It can leak out before it ever gets too hot in deep waters.
Riskin believes methane production at ocean bottom outpaces diffusion in deep, still waters. But another problem is the need for a large ocean region stagnant enough to allow methane to build up over time.
Most people think that the oceans, that the overall ocean, the majority of the ocean, would never become that stagnant.
Professor Riskin, however, is steadfast in his belief.
I have almost no doubt that there is a stagnant basin somewhere where methane is accumulating as we speak. But I have no idea where it might be, simply because the deep ocean is very little known.
Another reason some scientists disagree with Riskin's theory is that its destructive firestorms come from methane clouds that stay low to the surface. But methane ordinarily floats away into the upper atmosphere. At the University of Michigan's Hydrodynamics Lab, Professor George Kling demonstrates the basic principles. He pumps methane into soap bubbles, which rise quickly, and then burn when touched by flame. But these bubbles rise because they contain pure methane.
If you take pure methane, it's lighter than air, so it will rise, just like pure CO2 is heavier than air and it will sink.
But in an ocean eruption, gas is mixed with microscopic water droplets. Scientists call it a two-phase mixture, and when methane is mixed with water, it behaves differently than pure methane.
Once the methane comes out, if it's truly pure methane with no impurities in it, it will start to rise. However, this gas-water mixture increases the density of the methane to the point that it won't simply flow away like a hot air balloon. Chances are it will be ignited fairly quickly in the atmosphere, and so you won't have to worry about it dissipating too much.
But a fiery gas explosion is not the only hazard we could face from methane in the ocean. Methane is also hidden away in a mysterious material called hydrate. Part water, part gas, it looks like ice, but it burns. It holds more methane in the world's oceans than anyone ever imagined. And if it is ever released, it could turn the planet into a searing hothouse. Methane bubbles up from the ocean floor in many places around the world. Sites where plumes of gas bubbles appear are called methane seeps.
These plumes may reach heights of hundreds of meters, but then they disappear because methane gradually dissolves in water.
In some cases, the gas comes from the sedimentary microbes that Professor Gregory Wiskin says may slowly generate enough gas for an oceanic eruption. In other cases, the methane comes from underground deposits associated with petroleum. This is the natural gas used for heating homes and cooking food. We usually have to drill deep into the earth to get it, but it sometimes leaks out from small cracks in the ocean floor.
So we're going to head to Trilogy Seep, which is due south of Colwell Point.
Dr. Ira Leifer studies methane seeps for the Marine Science Institute at the University of California, Santa Barbara. He is examining how much methane released from the sea floor stays dissolved in the ocean water, and how much bubbles to the surface to be released into the air.
These bubbles saturate the water, kind of like your Coca-Cola. And the methane can't go into the water anymore after a while because there's so much methane in the water.
Here, the shallow waters and active currents allow the methane to bubble out, instead of being trapped under pressure.
Methane's buoyant, so it rises very rapidly. And right now, there are, one could say, an invisible smokestack of methane that's rising up into the sky above us.
As his boat floats over the seep, Leifer keeps a careful watch on just how concentrated the methane around him is.
We're measuring about 4 ppm, 4 parts per million methane in the air around here, which is about twice background because there's a lot of seepage, but pretty low. Now we're over an area with more bubbles. We're up to 6 and 7, up to 10, okay, up to 20, 30, 50, up to 55 ppm.
In just minutes, the measurement jumps from 55 parts per million to 5,000 parts per million. Still, there would have to be 8 times more for the flammable gas to pose a danger.
One reaches the lower explosive level for methane at 4%, which is 40,000 ppm parts per million. In the plume that we've been looking at today, right here, the methane levels are not high enough to be ignited. However, when puffs of methane comes up, we do reach the lower explosive level. In such a situation, if you're smoking a cigarette, you'd be okay, but don't light another one.
Bubbling seeps of methane gas may also come from an unusual material called methane hydrate, a little-known substance that forms in ocean depths below 500 meters, which is 1,600 feet.
Methane hydrate is a frozen form of ice in which methane gas is trapped in the ice matrix.
Hydrate starts with methane gas dissolved in seawater. When the water freezes, it creates a rigid cage of ice molecules around each methane molecule. The process takes place only at the low temperature and high pressure of the deep oceans. The result looks a lot like normal ice, but if you put a flame to it, it burns. Hydrate could be an immense source of natural gas for the future. Natural gas is normally pumped out of pockets deep underground, and the supply is limited. But vast deposits of methane hydrates are buried in coastal ocean sediments. The amount of methane trapped in hydrates may be far more than is known to exist in the ground.
It's estimated that the total methane available in the ground in the United States at the rate we're using it is about a 70-year supply. If we could harness all of the methane in hydrates in the continental U.S. waters, we would have a 3,000-year supply of methane. It's a vast quantity of methane. So this is of great interest. This is also of great concern because we must be careful that in the process of extracting this methane for use, we don't accidentally release it into the environment and create a catastrophe larger than we're trying to prevent.
The existence of methane hydrate in the world's oceans is another reason why Professor Riskin's eruption theory is unpopular with other scientists. Here's why. Down to 500 meters below the ocean surface, methane dissolves in water, but not in concentrations enough to erupt in violent gas fountains, as the theory predicts. But below the 500-meter level, something happens. The methane no longer dissolves in the water, but turns into solid hydrate instead. For an eruption to happen, methane has to be dissolved in water, like CO2 in the champagne bottle. If the methane turns to hydrate instead, it stays locked up in its ice cage, and an eruption may not be possible.
We cannot get too much methane into water before you precipitate hydrate, this solid phase. It's very, very difficult to conceive an ocean where we have supersaturated conditions in the water because we can't do that today in the lab or in the modern ocean.
Hydrates form at the low temperature and high pressure of the deep ocean, according to the laws of thermodynamics. But Professor Riskin believes there is more to the story.
Thermodynamics is a very tricky science. Thermodynamics does not tell us how long it might take for the dissolved methane in the ocean water to precipitate as methane hydrate. And according to some calculations, it would take longer than the age of the Earth.
Although hydrates float just like regular ice, they typically stay deep underwater, trapped in seafloor sediments, where they lock up much of the ocean's methane. But an earthquake or underwater landslide could release the hydrates. And if that happens, methane can escape in massive quantities.
And if you don't maintain them at high pressure and low temperature, they suddenly turn into gas, potentially explosively.
Gas escaping from methane hydrates may look something like this. The molecular ice cage breaks down, releasing pure methane gas into the water. If large amounts of methane hydrate are shaken loose from their sediments, gas could escape in dangerous amounts.
If a large amount is released and dissociated at 500-meter level, then that parts of water containing a lot of gas would be able to erupt, similar to a lake eruption process.
Even if the process is not a series of violent fountains, as in Lake Nyos or Riskin's ocean eruption, large volumes of methane suddenly released into the atmosphere pose a different danger. A catastrophic methane release from ocean hydrates could kick global warming into overdrive.
Methane is a very potent greenhouse gas. In fact, it's 25 times more potent than CO2 on a molecule-by-molecule basis.
As a greenhouse gas, methane can make temperatures go up on a worldwide basis. In fact, there's now evidence that methane may have caused the worst planetary heat wave in Earth's history.
It was extreme warming and it was global.
It wasn't the mass extinction 250 million years in the past. Instead, it was far more recent. 55 million years ago, a massive methane release kicked up the Earth's temperature. The sudden change in climate turned evolution on its head and set the stage for the arrival of mankind. In 2001, NASA scientists used computer simulations of Earth's ancient past to look at the role of methane as a greenhouse gas in changing the prehistoric climate. They suggested that movement of Earth's tectonic plates caused a large-scale release of methane from the ocean floor. Unlike the sudden disaster that may have caused the Permian mass extinction 250 million years ago, methane may have been released over hundreds or a few thousand years and caused global temperatures to skyrocket. It took place 10 million years after the disappearance of the dinosaurs, as the Paleocene epoch was ending and the Eocene was beginning. It was a time of sudden climate change, now called the Paleocene-Eocene Thermal Maximum, or PETM.
The PETM is a period of extreme and abrupt global warming that happened about 55 million years ago, where the Earth warmed by about 10 degrees Fahrenheit at least, in a period of only about 10,000 years. So that's geologically very rapid.
The methane that caused the temperature spike disappeared long ago, but scientists believe it was there because it left behind evidence in the form of carbon. Besides 4 atoms of hydrogen, each methane molecule has at its center a single atom of carbon. In methane, the central atom is carbon-12, which scientists call light carbon. But that element has another stable form called carbon-13, also known as heavy carbon. When paleontologists examined the ancient sediments from the PETM, they found much more light carbon than the environment normally has. The increase in light carbon, they suspect, came from methane.
Methane has drawn increasing amounts of interest lately because it contains very light carbon. And when people look at sediments, they find this light carbon signature.
The simplest interpretation is an enormous amount of carbon that was enriched in 12 carbon entered the ocean and atmosphere. The explanation I favor is that it's methane coming out of the bottom of the ocean. It's this large reservoir of carbon that is sensitive to pressure and temperature changes.
The large reservoir of methane was locked up in the frozen methane hydrates that were buried in the sea floor, just as they are today. But just what happened to unlock them is uncertain. This is what the world looked like at the juncture of the Paleocene and Eocene epochs. The continents look familiar, but Earth's tectonic plates had them on the move. India, for instance, was in the process of smashing into Asia to form the Himalayan mountains. The ocean floor was uplifted in these movements, and this is what the NASA scientists suggest may have shaken loose methane hydrates, releasing methane as gas.
Sometimes these changes trigger either uplift of big areas or especially trigger changes in ocean circulation. And either one would warm and destabilize seabed methane.
The methane would have bubbled out of the hydrates and reached the atmosphere, where it would gradually break down to form carbon dioxide.
Methane and carbon dioxide are both powerful greenhouse gases. They elevate the temperature. That further destabilizes more of the methane. And pretty soon you have a runaway process going until you've exhausted the methane that's built up.
The worldwide temperature boost changed the face of the planet.
If you were to come to Earth during the PETM 55 million years ago, you would find that in Wyoming, rather than having very dry and arid conditions, you would have vegetation that was more similar to what you find in Panama today. Subtropical forests, very lush.
This is the time where horses and primates, our ancestors, and several other groups of modern mammals first appeared.
The warming Earth sent evolution into a new direction, one that would produce new species, leading directly to the ascent of man. Thick forests extended into the Arctic, and strange dwarfed animals flourished. But environmental change at the Paleocene-Eocene transition had its losers as well.
We come into the Paleocene-Eocene boundary and the bottom of the ocean, it's a mass extinction. Many of the organisms go extinct, and that's it for them.
Warming of the scale seen in the PETM would be considered a global catastrophe if it happened today. But if Gregory Riskin's theory is correct, and the methane release comes from the sudden explosive eruption of a stagnant ocean basin, the disaster would be swift and far more violent.
It's a huge fountain, and a huge amount of methane would be expelled from the ocean through those fountains.
Few scientists agree that a global-scale eruption in the open ocean is likely. But there are other bodies of water where the phenomenon may occur on a smaller scale. The Black Sea, for instance, is being studied today for its methane content.
The Black Sea is essentially a stagnant basin. Since Black Sea is accumulating methane right now as we speak, it's easy to guess that it was doing it a long time before, and perhaps it was doing it for, say, a few 100,000 years.
In fact, some scientists believe a deluge 7,000 years ago in the Black Sea gave rise to the Bible's account of Noah's flood. Professor Riskin describes the night he found a parallel to his methane theory in the book of Genesis itself.
I went back home and found the place, Genesis 7:11, and I read the sentence which says, "On that day, all the fountains of the great deep burst forth." And I was amazed, because that's exactly the picture which I have for my methane-driven eruption.
Methane concentrations in the Black Sea today are nowhere near enough for another eruption soon. More likely, according to Professor Riskin, is an eruption on a similar scale, perhaps an area the size of California. But it would happen somewhere in the open ocean, where the deepest waters are twice as deep as the Black Sea. That means the water under higher pressure could store even more methane, holding the potential for a global disaster. The long history of life on Earth is separated into periods, epochs, and other divisions, each marking an extinction or other change in evolution. The smallest of the divisions is the geologic stage, and the boundary between every stage is a target for the methane eruption theory of Gregory Riskin.
I think that every single stage boundary, which is marked by a large or small mass extinction, is actually a result of a catastrophic event. And I think that this catastrophic event is a methane-driven oceanic eruption, because there is no other simple mechanism on the Earth which would lead to this kind of repetitive wiping out of most of the life on the whole planet. Over the last 500 million years, there are about a mass extinction every 1 or 2 or few million years. The last oceanic eruption probably happened about 800,000 years ago, which means that we may be overdue. And so we don't know whether it should happen tomorrow, or 1,000 years from now, or 5,000 years from now. We don't know.
We also don't know where it could happen. Other scientists agree with Riskin that our ocean bottoms are not well known. So if a stagnant methane-bearing basin is out there, it has not been identified.
The entire seafloor has not been very well explored. We don't understand all the processes that occur down there by far, and research is difficult, expensive, and has not been receiving proper funding.
Without knowing where there are stagnant basins on the ocean bottom, the site of the next eruption, should it occur, could be anywhere. A methane eruption in the Pacific, for instance, could put the entire west coast of the United States in danger. It would begin in the deepest part of the ocean, as water saturated with methane may be shaken by an earthquake. Once the gas begins bubbling out, there would be a chain reaction, forcing fountains of methane and water to the surface, across an area the size of California.
This gas-water mixture, which is produced by the fountains, would be rolling away from the place in all directions, on top of the surface of the ocean. It would be rolling with a great speed, so tsunamis would reach the west coast of the United States, for example, and say Hawaii, in a very short time, perhaps a few hours.
2004's Indonesian disaster raised tsunami consciousness on the west coast. North of San Diego, the city of Encinitas has tsunami warning signs posted near the beach, even though the risk here is considered moderate. But that's because most tsunamis are caused by earthquakes. This one would be very different.
The tsunamis would not just be a one-shot thing as they usually are. They would be coming on continuously, days or maybe weeks.
A small-scale simulation in a tank at the University of Michigan's Hydrodynamics Lab illustrates the tsunami effects of the continuous methane fountains. Instead of one or two waves generated by an earthquake, the methane fountains would send wave after wave against vulnerable coastlines for as long as the eruptions last. Cascading tsunamis from a Pacific eruption may first strike American shores at San Diego. The low-lying terrain exposes heavily developed areas to extensive water damage.
It is possible to estimate the flood waters may reach heights of over 100 meters in a large eruption.
At that height, tsunamis would cover downtown San Diego, leaving only the city's 25 tallest skyscrapers visible above the water. The tsunamis would hit other exposed cities as well, where whole populations would face the sudden disaster. In time, the entire world would be affected, as methane bubbles make ocean volumes expand to push up sea levels around the globe.
The total sea level on the globe will increase by about 35-40 meters.
The methane in the water will take months to bubble out completely, keeping sea levels as much as 130 feet above normal. The world's coastlines would be visibly altered as the oceans push inland, flooding wide areas of densely populated cities. In scenes reminiscent of Hurricane Katrina, millions of people who survived the tsunamis would be driven from their homes along every coastline in the world.
About 25% of the population of the Earth lives in the coastal area within 100-meter elevation from the sea level. So 25% of the population of the Earth would really could be affected by an eruption like that just from tsunamis and the floods.
But floods and tsunamis are only a beginning. Next would come the methane-bearing water clouds, ready to ignite as soon as they meet any random spark. Firestorms of methane would follow the tsunamis to all the West Coast cities, and any place else on Earth where air currents carry the volatile methane clouds.
I estimated that even in a reasonably small oceanic eruption, this explosive mixture will be able to cover the whole surface of the Earth with a layer of about 50 meters thick.
The methane eruption itself is confined to one area of the ocean, but the disaster it produces would be global. Though billions of people could perish, mankind may escape utter extinction.
I'm confident that a large part of the population of the Earth will survive, but the damage will be of a scale which has not been observed ever.
The scenario drawn by Professor Riskin is almost too extreme to contemplate. Although few scientists agree with him completely, some are keeping an open mind.
The mechanism that he proposed may not be correct. And so there are some details that may not be correct. The main hypothesis is still a good one, a very plausible one.
A theory that predicts disastrous methane eruptions on a regular basis may seem improbable. And if only a few find it plausible, does that make it worth serious consideration?
Even if there is a small chance that such a thing will occur, the consequences of it are so disastrous that it certainly deserves funding on all levels. Only the global nuclear war, perhaps, compares.
Even if global catastrophes are rare, ours is a planet where we know such disasters have occurred in the past. With that as their motivation, scientists worldwide will continue to search for clues to understand why they happened, hoping they may learn how we can survive the disaster